Go for it.
Good morning. We are the Fourth Axis, and welcome to our final capstone presentation for our foldable 3D foldable and transportable 3D printer. We're gonna introduce ourselves. Yeah. I'm Nicholas Trott. I'm the team lead for this project.
I'm Mateo Santos. I'm the treasurer for this project.
I'm Nick Butcher.
Rashad Stubbs.
I'm Dennis Martinez.
You won. Theodore Andreza.
I'm Eduardo Manson. I'm the secondary lead for this project.
Oh,
Want to go?
feels like. There we go.
There we
That's
go.
working fine.
These were a few of the main key product specs given by the customers that pretty much guided our design process. Having a weight constraint 12 kilograms, dimensions 8 by 16 by 21. It had to be assembled in under 5 minutes. Required no loose fasteners, and a print volume of 18 by 18 by 18 was also met. The fourth axis is driven by a strong passion to transform the Prusa Mini Plus to a foldable autonomous 3D printer, capable of large-scale part productions requiring very minimal maintenance. We create top-tier part ejector and foldability add-on kits for the Prusa Mini. Now, our solution is simple yet innovative, but through this innovation, we're able to maximize our customers' 3D farm print profit by eliminating human intervention from part fabrication.
Yeah, so looking now at testing deliverables, we started with the assembly test, and by all accounts, it was a success. We met all customer requirements, most notably the assembly time. We were able to assemble in 2 minutes and disassemble in 1 minute. And the weight requirement of 12 kilograms, we just about met that at 12 kilograms. And looking at these pictures, on the left, you can see the printer disassembled with all its components in the foam case. And then on the right, the final printer assembled. And then next, jumping over to the denomination test. For this one, we actually found some inconsistent results. So what we did is we tested 5 different geometries using both PLA and PETG materials. And we actually found that about 50% of the tests were successful. And we saw that the ejector arms seemed to struggle more with parts that had a larger surface area and smaller heights. So if you jump to the next slide, I'll show you all the geometries we tested. So we had a cube, a flat plate, a hollow cylinder, a tilted piece, and a triangular pyramid. And notably, the top 2 pieces were the ones that struggled the most, the cube and the flat plate. And because of these results, we actually did a 3rd round of testing. Chad's gonna talk about.
Yeah, so due to the inconsistent of the delineation test, we did we did a surface area to height test ratio. Basically, this is the PLA results. This is the before and after. For the PLA part, it was able to successfully delineate with maximum ratio of 46. And this is the PETG ratio. And PETG ratio we actually successfully delineate for every part, so up to a maximum ratio of 250. And the main reason of this ratio gap is due to the rough texture of the steel sheet. Since the delineation process occurs after it's completely cooled, the parts goes under shrinkage, which reduces the first layer adhesion.
So this is a little quick video. We're not going to watch the full thing, but this is one of our performance evaluation metrics, the assembly time, which in this video is shown as 2 minutes and 7 seconds. We mentioned earlier, we're hitting about 2 minutes consistently, just on average. So we're not going to watch the whole thing, but you can kind of see the process required to attach the pieces together. Could you just
skip forward?
Yeah, skip a little forward, please.
Yep.
Yeah, and this is just a quick little summary, which we can get more into detail later on. But yeah, so to fast forward, this is kind of what the assembled version looks like. You can hit next.
Just gonna show.
Sure.
You're averaging about half of the required time for the assembly and disassembly, which we were very happy about.
Yes.
Yeah, disassembly even faster.
Yeah, so that's where disassembly comes in. So here we have 1 minute and 7 seconds. Like I said before, we're hitting about an average of 1 minute. And yeah, it's basically the exact reverse of the previous video. You can kind of see how this back plate, I don't know if you can see me, but the back piece slides off really nicely. And then this pin right here gets taken out. everything collapses into a really nice shape that we can fit into our box.
And it's to be noted, within the customer needs of no loose fasteners,
Yes.
that this pin connecting the ejection assembly does connect to the 8020 on the side of the printer via a lanyard, so it won't be lost. As well as the screws that disconnect to hold on the support box for the extruder arm. All of those screws and their T-nuts slide out and are able to maintain contact with one another so as to not have a loose fastener when you disassemble the printer.
Yes. Here's a little quick video of our ejection and delamination. The times for these vary very heavily. They have a lot of variation is what I'm saying. And that's all a function of the input speed of this motor turning this lead screw right here, if you can see that. That's something I can get into a lot more detail later, but a lot of thought was put into that. I think here we're running at 120 RPM, but our expected RPM would be between 80 and 100 just to get that maximum torque before we see a major drop off. So here, I think we're consuming about 80% of the maximum torque that this motor can output. We're not doing 100 simply for sake of speed. And as you can see here, the time to get across the plate and back is approximately 10 seconds. You can anticipate that to be closer to 5 minutes for some of our larger parts that have a lot more surface area and therefore require a lot more torque and force to remove from the plate.
Yep. So this is the cooling and cube process. This video is about 2 minutes long. It shows a print and then the cooling process, ejection process, and then it automated starts a new print in the queue. And so you can see right now it's printing. This is fast forward and then it moves to the back, which normally there would be a cooling fan right here to cut down on the cooling time before delamination. And this is all automated. There's no user input allowed, and the queue goes up to 50 parts, so you can print up to 50 parts automated. May take a little bit of time here. This is sped up a bit, but
You want to talk about like the cooling heat transfer?
yeah. So for the calculations, I calculated that would be about half the time. It usually takes about 6 minutes to cool down at 35 degrees Celsius after a print, but with the cooling fan, it should take about 3 minutes, maybe a little bit less. So this is it heating up again after I simulated ejection with my hand just because we had to bring this home and the case wasn't finished yet. But yeah, so it already went through ejection, cooling, and now it's starting the new print. This is the purge line. We consider removing the purge line, but it kind of messed up the prints because the nozzle would tend to get crowded and it basically all stick together and it wouldn't print successfully. So that intro line is essential, and now it's starting the new print. This was all automated using Octoprint software. And it'll basically do the same thing as last time. It moves to the back for the cooling, and then it moves forward for the ejection. And you can go to the next slide. It's basically the same thing.
Cool. All right, so here's some design highlights and key features of our product. As we said before, the foldability is a huge thing. Disassembly and reassembly, we fell well within the 5 minutes required and the customer needs. There are also no additional tools needed for any of that process, so no loose fasteners, but you don't require screwdrivers or any wrenches or anything to take it apart. It's easy to do by hand using thumb screws. It fits into this case for easy transport and ergonomic transport. It's pretty easy to carry, weighs about 12 kilograms exactly, so hitting the weight specs as well. And in terms of the part ejection, it delaminates and auto ejects all parts we tested within that surface area to height ratio, depending which plastic it is. So if PETG performed with a lot of reliability. The original printer remains collision free, and that was an important part of our design. We couldn't have any of the motors that drive the printer be responsible for the delamination, for risk of burning out those motors or having issues with the calibration of the printer as a result of that. So all the torque, all the strain on the motor is put onto an external motor. So if there was something to break, it wouldn't compromise the actual function of the printer itself. And during all of our test prints, there were no issues with the parts. It maintained high precision. It got good first layers, and any print failures were really just due to like minor technical issues or with the surface area for the ejection. You want to go to the next one? Yep. All right, so looking at competitors, currently there isn't another printer on the market that has both features that ours has with fully automated printing as well as the foldability. We've seen other continuous printing systems out there, many of which use a print bed such as this, where you can print multiple parts and roll them off as they go, or print long parts. And there's also very expensive non-belt systems, but neither of these are fully automated processes. Otherwise, in terms of foldability and disassembly, the whole features with no loose fasteners and having a custom case for the product are unique to our design as well.
So yes, these are the antlers. You can see on the right picture here, that little black line there, that is the antlers, and it basically keeps the print bed stationary during the print because it needs to delaminate from the print sheet, the part does. So by keeping the print sheet stationary, it allows for better delamination basically.
Yeah, we had in many of our first tests, when you had like a larger part, it would just have too much strong adhesion and the entire bed would actually demagnetize and slide off. And originally we did have a bit of concern with having a 3D printed part being a support piece for this. But since it doesn't come in contact with the bed until after the bed is cooled and pressed against it, throughout all our testing, we never had any thermal compromise to this piece. It never melted and had never had any issues. And it keeps a 5 millimeter gap about off of the edge of this plate, so it doesn't interfere with the printing process, and it's not in contact while the print bed is hot. Okay.
So here are the antler calculations. It's basically a cantilever beam since it connects to the side of the 80-20. That's the only connection point, and then it's pushed about a moment at the top. So here there's the moment of inertia, and then the maximum stress would be about 12.8 megapascals. And the yield strength for PLA is about 42. So there's a factor safety of about 3.3.
And we noticed no deformation with the part either in any of our testing.
So these are, this is for fatigue. I found a fatigue curve for PLA 3D printed from a research paper, and I found the maximum strength, or the strength that it would, the maximum strength that it would find during the print, and then the ultimate strength, and then we found a ratio and plotted on the graph, and it would take about 10 to the 5 cycles. And I also did some calculations to where if you were to print about 10 parts a day, every day, it would take about 30 years for it to reach 10 to the 5 cycles. So that's a pretty long, the antlers itself have a pretty long life in terms of the printer.
And then the other good thing about the part is if it were to break in an unpredictable fashion, you could print a new one easily. It would only compromise the automated feature temporarily. You could still use the rest of the printer without issue.
So moving on to the foldability aspect, we, like Nick said, had T-nuts and thumb screws that went through these flanges on the electrical box and slid into the 80-20 of the printer. There are forces present on these flanges on the electrical box, which led to some we had to consider the forces on it to make sure that the PLA that is printed out of did not yield. So if you move on to the next slide, you can see those calculations. Basically, this is we took the axis that is present on the x-axis and we converted that to a force, found the stresses present on the bolts due to that force, and then we compared it to the yield strength of PLA, which, as you can see, these stresses are way less than the yield strength of PLA. So there's no concern with the electrical box flanges yielding due to the torque you need to give the bolts or the thumb screws to hold the box to the 80-20. Go ahead. Next, we have the actual cantilever beam that is present due to the ejector assembly. There's going to be a force present on this cantilever beam since it hangs off the side of the 80-20 of the printer bed, which you can see the calculations for that on the next slide. This is the deflection formula, and it involves a moment of inertia. There's two assumptions done here to be taken into account here. We assume that the 80-20 is a solid square cross section, and we also assume that the force present due to the weight of the x-axis is a point load concentrated force. We did that because it's a conservative estimate. If it passes that test, it can pass a distributed load. So you can see that the deflection is very minimal, 2.68 times 10 to the negative 2 millimeters. So basically no deflection at all there.
We did good too, because we keep a very small gap between that piece and the print bed to ensure we delaminate all layers of the part.
So this is the evolution of our design. Initially, we were doing the Prusa i3 MK3S Plus, which is a bigger version of this 3D printer. Nick S had this garage door print bed idea, which would continuously rotate the print bed and eject and delaminate the part. However, this was way out of budget and way too difficult to implement on that printer. For the foldability on this, at this stage, we had the taunt hinges by Nick B. This design would tackle the foldability aspect. However, the taunt hinges, you couldn't give it enough torque to secure the actual Z-axis assembly as strongly as you needed. So we were worried that it had too much play and would mess up the calibration and the prints themselves.
And actually, with addressing that topic, that's why we decided to have the slide away for the disassembly anyway.
Yeah.
Pretty much any hinge that we looked at for the thing, it became a really big issue to actually keep the extruder axis stable enough to guarantee print quality. And it would have either required a bunch of extra material to support it that got us out of our size or our weight requirement. So we decided the partial disassembly was the best way to go, and it's been very stable and high quality for us.
So we switched to the Prusa Mini, and this is the ejector arm. It started off as one solid block, however, it's too big to be 3D printed. So we changed it to 2 individual pieces. We also changed the thickness of the ejector head after a consideration taken in from Dr. Trom. We also increased the height of the ejector head so it could clear the print bed easier and delaminate all pieces. Continue.
Yeah, or also the height as well was increased that way for the maximum build volume, that's 18 by 18 by 18 centimeters. It wouldn't have any risk of overly tall pieces falling backwards and onto the designated bin.
And lastly, Nick B found this mechanism during his research when we were switching from the MK3S Plus to the Prusa Mini, which inspired our design. This would be outside of our budget, but this is a great alternative, which allows us to just fold the entire Z-axis assembly completely. And yeah, continue.
This one's unique. Here's the electrical stuff.
Oh, yes, sorry. Okay, so here's kind of a quick little glimpse of the electronics, which can be seen on the current model there. I don't think it's visible in the camera, but we'll go over that later. So to use for this electronics setup, we basically have an Arduino Nano because of its compact size. We have a driver, which right now we're using the A4988 motor driver. All of that is soldered and connected onto a 3 by 7 centimeter perf board, which is mounted to a configuration of standoffs that are on the front of the printer. Underneath that, we have a voltage reducer. So currently we're powering this with a wall power supply. So we're getting 12 volts from the wall, and we are feeding that 12 volts into this driver here, which turns it into 5 volts. That powers the logic of the Arduino. And then it also throws the 12 volts into this other motor driver, which the top motor driver is for the fan. So we're turning 12 volts into 5 volts for the fan as well. And here you can just see another little glimpse of, we used heat set inserts so that we wouldn't have to be threading into 3D printed plastic. Heat set inserts are just a great alternative to threading into plastic because they give some good structure, and you can melt the plastic as you're inserting them. And as the plastic resolidifies, you get a lot of additional strength because of the knurling that's on the inserts. And I think that summarizes it well. The same thing can be said over here. This is just a little exploded view of the rear plate. So
Yeah, it's noted that this entire thing is just one 3D printed. We modified the front plate of the printer to add on all these features to support our electronics in a box that kept it open. You could fix any problems you could see with it.
correct. Yes, the original 3D printer files were all adjusted in some capacity. So all of these parts that we're seeing here are 3D printed, except for, of course, the 8020 and the 3D printer itself. So go ahead.
Yeah.
For the back plate, we actually cut off a portion of here so there's no interference with the electrode box. And we also create like a hole for the T-nut to insert here so it can be screwed in with the thumb screw of the electrode box.
And in a more permanent application, this T-nut would probably be just glued in, so it wouldn't risk falling out.
Yeah.
It seems pretty stable in there now, but obviously for us modifying the design, we didn't do that in our model. Okay, looking at some of the rest of the features of our CAD design. This part here, I designed to hold on the ejection mount. So it's essentially a sleeve that supports the 80-20. And the 80-20 piece we have that supports the entire thing, we drilled a hole through here. So this allows the pin connection to support this and be easily removed. So you can just slide it in, mount it, it locks very stable, and then you slide it out. And that's what's responsible for a very quick disassembly time. In terms of the ejection pushing arm, this shows a better exploded view of how it functions. It has inset in it the thing to stay on the lead screw motor, as well as 3D printed guide rails that slide along the 80-20 that are integrated into the tail of the part. And this front piece is just the support to hold the front end of the lead screw just so that it doesn't lean forward or anything, keeps it in the right place. And is there anything you're talking about? No, that's all this.
This is the motor mount.
Yeah.
Oh yeah, this is the motor mount to support the back of the NEMA motor with the lead screw. Which is the same thing, it fastens on with 3 different nuts on the back of the 80-20 to provide a stable foundation to give us enough force to push all of our parts off effectively. We never once had an issue with the ejection assembly coming apart or with any of the parts we try to delaminate. Okay, looking at the upper half of the assembly, we modified the electrical box to give us the ability to do our rapid disassembly and assembly to slide on and off. So originally this box would mount more permanently and the metal support plate used to overhang and also mount atop the 80-20. To change that, this is our, really I think the only part we had that was modified that isn't 3D printed. We had to water jet and alter this plate so that it only sits to the length of the box. That way it doesn't interfere in any way with sliding off the 80-20. This assembly. And for the ejection, we had to move the user display so that it wasn't sitting on the edge of the printer where all parts were disposed and pushed off. So we got a longer connection cable for it and we mounted it on the outside of the upper extruder arm, such that it does not interfere with the extruder in any printing process.
Another thing to mention as well is that the current location of the user display is placed in a way that it is right next to the bin area where the 3D printed pieces would fall after ejection. So that way you don't have to look between 2 different angles to select your prints to go and also see where your prints are after they're delaminated.
Okay, this is a better in-depth look at the electrical box. So as we said, there's an inset T-nut in here to support the back thumb screw. And just a regular T-nut sits within the 80-20 to support this screw here. And both of these screws have adequate length such that when this one is removed, you can screw it back in to keep it stored at the part. You don't risk losing it. This screw here on this T-nut, you can loosen and slide it off without having to fully unscrew any of it. So it would still stay together and not be a loose fastener. I addressed that same thing with the lanyard securing the support pin here. But this also gives us a view of the fan assembly, which is simply a support piece that holds our fan. And it clips inside of the 80-20 rail using the same mechanism that the antlers use to support on the other side of the plate. So that is very easy to put on and put off, and it has no really no wiggle room. It uses the actual bottom of the surface to support the fan in the same way that the antlers do, which provide a solid foundation for it. And this is a full view just showing the connection of the ejector subassembly. As I mentioned before, it might be hard to see, but there's a hole through this 80-20 here. And that's aligned so that once the edge of the 80-20 hits the edge of the printer's 80-20, the 2 holes line up, and that's how the part is fastened and secured to the side of the printer. All right, here's another view of the antler. As you can see, same mechanism and same idea that we used for the fan clip reduced inside. And the same thing is that the bottom of this also will sit on the bottom surface that the printer rests on to provide the stability needed for this to function optimally. And this is a better exploded view showing the ejector head and tail. As mentioned before, we made these 2 separate parts so that if there were any issues, if it broke, you can still actually print them and restore them. It was too large to print within one volume, even on the larger Prusa printers.
Another thing to know as well with the antlers is the reason why there is a gap in the middle is because if we had filled that gap entirely to kind of go right next to the entire edge of the print sheet, it would have prevented certain pieces from successfully leaving the print sheet and falling to a bin. We had that issue, so we kind of met part way. It only takes up about 10% of the print sheet length. So as long as our customers put their pieces in the standard location, when you put in the slicer, which is the center of the print sheet, there shouldn't be any issues with ejecting pieces. And for bigger pieces, if it takes up the entire length of the print sheet, there also shouldn't be any reason for it not to be able to fall over that small distance that's blocking. Yeah, so this now goes down to the cost table summary. Basically, what was first done is I investigated from the US Bureau of Labor Statistics. In Florida, in May of 2022, I found in the production occupation industry, what was the average pay, included over here is the average hourly pay. For the benefits, that was taken as 50% of a single employee's hourly rate. And the overhead, which is the cost of the facility, was estimated to be about 200% of the hourly rate. And those were added all together to come up with the $62.23 hourly wage for a single employee to work. Here, we actually consider two approaches to where we could sell this. One of them could just be the assembly kit, such as the ejector arm, the fan clip, the new electrical box, the new display. These pieces would be given to customers that already have pre-existing Prusa Mini Plus printers so that they can attach and make their own modifications. The second iteration, which is the one on the bottom, is the pre-built printer, where we give them the Prusa Mini Plus printer already pre-assembled with all the pieces attached and the carrying case. This model is somewhat similar to the model that the Prusa company uses as well, where they sell a pre-assembled kit or they sell it as individual pieces that the customer builds themselves. The following time estimates for each step, such as just drilling the hole into the 8020, cutting a rubber sheet and gluing it to the riser, which is underneath the ejector so that it's at a stable head level with the print sheets. Soldering, wiring, assembling electronics, setting up and transferring code, and then finally just 3D printing setting up the 3D print, like starting it, collecting after it's done, cleaning it. Those were estimated based on times that we have spent so far to complete those steps. And those were used with the $62.23 hourly rate to determine an overall in-house manufacturing and assembly costs. The only additional step that was included for the pre-built printer was actually us ourselves assembling the Prusa Mini, which we decided to buy ourselves disassembled since it is a cheaper option. And we would have to disassemble it either way if we want to include the electrical box, new back plate, front plate. And yeah, that was estimated to take about 8 hours to complete. Moving on to the next slide. Mixed over here, I have for the two models, there is two approaches as well. The cost for a single prototype to be built, or the cost for a production scale run of units, which was estimated to be about 10 units we're estimating it to be. The total consumable material cost you can see over here is basically just filament to use, PLA to print all 3D pieces, any fasteners, the 8020 rail, the thumb screws to attach it. The outsourced manufacturing, so I previously shown you the in-house manufacturing and assembly costs. That was added to an outsourced manufacturing cost that we did for the water jetted metal plate. Due to some calculations, we determined that it would be cheaper to actually outsource that to Xometry rather than us building it in-house and also having to buy a water jet machine ourselves. Adding that, we also used USPS for an estimated shipping and handling cost to transport our product across Florida. We basically assumed in our product that we'd be building a facility inside Florida, since our primary customer would be UF. So that reduce shipping costs. If we ship to places outside of Florida, we'd have to reestimate these prices based on the weight and the actual dimensions of the pre-assembled kit or the pre-built printer. But as you can see, for one prototype, it came out to about $1,005.39. And for a production scale run, this price isn't exactly a ×10 of the one product run, because for many things such as fasteners, thumb screws, and things like that, you buy them in packs, multiple packs of 100 or 10. So we don't use as many for one piece. So we have additional pieces that just go towards the other assemblies. And the pre-built printer, it actually jumps up to about $2,190. This spike in price is, of course, by the original Prusa Mini Plus printer, as well as our carrying case that we would include for customers if they bought our pre-built printers. And the same could be said as fact for the production scale run of pre-built printers. It's not an exact ×10 of the cost, because we do have leftover materials that we can use to build the rest of the printers.
Okay, so overall, this is pretty much all the key features of our design. I think generally we've kind of ran into a lot of problems that we've had to find unique solutions for, but we've implemented most of our ideas with pretty good success. I think really the biggest shortcoming of the project is not having a full reliability with delamination, particularly with those large surface area PLA parts. ideally, if we wanted to improve the design in the future, we've discussed doing more testing and trying to find maybe a way to thermal shock the thing more. Just some, or even just use only PETG beds to ensure like a higher rate of success with delamination. What are some of the other design improvements?
I have one. One of the big design improvements that, well, there's actually a few. A lot of the biggest battles are fought in the electrical side of things, particularly that when you mentioned the strength of the delamination reliability. Right now, we're using a servo motor, stepper motor with a 1-to-1 gear ratio. We have a very strong interest in switching that to a 1-to-5 gear ratio, so that we can have, a slower speed but much higher torque, 5 times the torque. And another thing, because we're running at slower speeds in that instance, it would be nice to have a driver that could handle the higher speeds. So, and we would switch from the A4988 driver to the TMC 2209 driver, simply for its higher capacity to run higher currents through it. Just as a reference, I think we went through 6 or 7 of these A4988 drivers just because they're not really built for the amount of current that we're running through them.
Okay. And yeah, leading up with those major design improvements that we see for the future. That's our presentation. Thank you for attending. We'll take questions now. You might have questions on.
You guys have your speakers on, right? So
Yeah, it should be working if they ask a question. Could they?
yeah, Tom and Isaiah, I'm not sure if you guys can hear us, but if you've got questions, you're up first.
Okay, yeah, guys, this is Tom Singer from Northrop Grumman. I guess you guys jumped right into your presentation, and it took me a little while to kind of get oriented. And I had an idea because I'd seen the customer needs statement from Dr. Traum, but I still don't know that I have an idea of what exactly it is that you were building, modifying, and on top of what. I don't feel like I ever got a real sense of that, so I'm not exactly sure kind of what the scope of your project was. Can you maybe detail that a little bit, maybe looking at that conclusion slide and pointing things out?
Yeah, of course. So generally the scope of our project, just to be clear as well, we chose to use the Prusa mini printer. Originally, we started with like the more standard Prusa MK3S, but to fit our foldability specs for the size and transport, we ended up moving to the mini. The overall scope of the product and the goal of it that we understood from the customer is that the idea is that these printers could be used to set up automated pop-up print farms. So for mass production facilities that lack brick and mortar capacity, you would be able to set up, and also that lack labor costs, you'd be able to set up many of these at once, have them easily transported location to location, and be able to have them mass produce parts with a very small amount of labor needed, like probably only 1 or 2 people to run like a dozen of the printers. So that seems like that was like the general goal of what we were designing. Does that answer your question?
Yeah, I mean, can you point out what on this picture is new design versus what is the original Prusa printer?
Oh, yes. Okay, so
and if you don't mind, could you guys drive the mouse, because I can't necessarily see you pointing at the screen as easily.
Oh, for sure. Is the screen shared?
Yeah, screen share.
Yes.
Yeah, use the mouse over there. It's on screen.
Yeah. We
Okay.
can see them out. Yep.
There
You have to look at it over there.
Okay, so this entire assembly arm here, this 8020, the NEMA motor, the motor mounts, this is all our added on ejection assembly, including that mount on the side. We also added on the fan and the fan clip supports. This is the antler piece we were discussing that supports the print bed to prevent it from demagnetizing and slipping off during part ejection. We custom this spool holder. This is something separate on the side, since we didn't have any space to have a mounted spool holder on our model. And
Okay, yeah, I was going to ask about the wine glass next.
yeah, that's what that is. So it's meant to be stable, and we've run all our test prints using this spool holder, and it's been rather effective as like a freestanding version. And the other main change was this whole electrical box setup, because this is the basis that supports all of the extruder arm to allow it to slide off and then fold forward to make it packable. So we completely modified this box design to allow for that slide off. And this metal support plate here is like the custom metal piece we had to have water jetted, as it used to overhang the 80/20. And actually I could probably.
Yeah. Yeah, that helps a lot understanding what it was you guys were doing.
Yeah, would you want to see a picture of the original just to compare the differences?
Yeah, if you got one handy, yeah.
I think we have one of the PowerPoint, right? Okay. Is it just screen sharing that way?
No, I'll do the screenshot.
Yeah, you can go ahead.
But yeah, like just find it over here. Gonna stop the screen share momentarily so I could start a new one to show the actual printer.
Okay.
Yes, here. So yeah, as we can see, the original display. Oh, is the screen share working for you guys? Are you able to see?
It's on Zoom.
Yeah, we can see it.
All right. So the original display was over here, Renix's side, which was later mounted over here. Basically, ejector arm will take up this left space that you see is not occupied. If we actually show it from this view as well, you can see this was the metal plate that extended all the way. The reason why we had to cut it off, as was previously spoken, is that it, when sliding off, if we had left it on top of the 80/20 in its original state, it would hit the back plate and it would prevent complete detachment.
Okay.
Yeah.
Okay, so I think I'm reasonably well oriented to what's going on now. So that's good. I would encourage you to think about that, especially where you're presenting to somebody who hasn't been following the design day by day. Think about those sorts of things. So the ejection mechanism. You guys are responsible for the ejection mechanism concept, or are you just implementing a concept that you were given?
No, we're
No,
responsible
we
for
designed
the
our own.
concept.
Yeah.
Okay, so that's your concept. My granted limited experience with 3D printing is the things don't like to pop off of the print bed without let's call substantial wiggling of the bed and maybe a little scraping between the bed and the part. How robust does your part have to be pushed off of the print bed? I mean, are you effectively limiting yourself to printing very solid things?
I mean, if you mean by robust, do you mean solid? Honestly, the best parts that we ran with our delamination testing was some of the very thin, the cylinder piece that we
Here, I can
showed.
pull it up over here.
Yeah, pull it up in the earlier slide.
We tested we were saying earlier the different geometries. So basically we tested some basic ones. Most of them were solid pieces. The only one that we did that wasn't was the hollow cylinder. But what we found as well that for if we had a more complex geometry, that for example this tilted piece over here, where the print arm would hit the higher surface first before it hit the bottom of it, that moment would actually facilitate delamination. So if you actually have more complex pieces and ones that you could orient so the ejector arm contact would happen at near the top of the piece and not the bottom of it, that would facilitate delamination. The hollow cylinder over here, as you can see, it only has a thin wall structure, and it was able to delaminate perfectly compared to the other solid pieces. So we assume that for any hollowed out pieces that have the low surface area to height ratios or just low surface areas compared to something like a solid flat plate or rectangle or anything that would cause certain moments with the ejector arm while delaminating, that would be sufficient enough to cause successful delamination.
Yeah, I'm just kind of I'm curious because the things that 3D printing makes sense to produce tend to be more intricate, right? If I need to produce that cube or that cylinder or that little I don't even know what you'd call it, right? But if I need to produce any of those shapes, I'm not 3D printing, right? I mean, 3D printing is something I'm going to do for something significantly more complex than that. And I wonder if you'll be able to successfully delaminate with your pusher mechanism without snapping, breaking things.
Yeah, for sure. More testing would have to be done to investigate the more complex and robust amounts. I mean, that's one of the biggest issues as well that we had previously thought about when we were designing our ejector and what system we wanted to use, is the fact that like with 3D printing, you have a near infinite amount, forgot the camera was there, near infinite amount of designs and shapes and geometries that you could do with it. So we agree as well that we'd have to do further testing to see its like actual limits.
And that's also
Okay,
why we
yeah.
switched the like steel sheet to the texture steel sheet, so the ratio went up to like from 46 to 250.
Yeah, our testing served mainly to kind of like parameterize the problem, which, you know, isn't perfect. More testing is required to really know if there's any other part geometries very specific that we should encourage customers not to print.
Yeah.
We know like we don't really want like brims printed on the thing, because the currently like the main dominating factor to whether a part adhered or delaminated was that surface area to height ratio.
Yeah.
So
Okay, and then I think. Oh, I'm sorry. Go ahead,
If
Isaiah.
you don't mind. Hey,
Go
this is
ahead,
Isaiah from
no,
Northrop Grumman. So I wanted to ask kind of on what Tom's getting at here. Did you guys do any sort of calculations for your motor sizing? Because I know the lab has a ton of NEMA 17s and just kind of laying around. We've used them in semesters prior. And I know like back when I TA'd for this class, a lot of times it was just like, you know, find the NEMA 17 in the lab that existed and like use that. Did you guys do any sort of motor sizing, or did you just use what was in the lab?
Right? Okay.
Torque.
Yeah, can you go to the?
Yeah, we're gonna
Yeah.
demonstrate over here a motor torque graph, which
So initially we went with a 1-to-1 motor, simply because it was, you know, the most available. It's by far the cheapest. And we'll kind of skip over this for now. So you're right. The 1-to-1 motor did struggle with some of the larger parts, and our response to that was actually switching to a 5-to-1 motor instead, just for that higher torque. So yeah, those were really the only two we sort of tested. In the future, we could also consider some of the higher torques. I believe we had a 27-to-1 that we were considering. But a lot of it, one of the driving factor, you want the higher torque, but we're also sacrificing a lot of speed, and theoretically, a 20.
Do you care about speed?
So that is that's actually a fantastic point. That wasn't mentioned in the customer needs, but that's something that we did care about, because we would be approaching the 45-minute mark to delaminate a single part. Just in that 45 minutes come from the time it takes to reach the other side of the bed with the current capacity, with the current speed that we can run the motor at. Does that make sense?
Yeah, I think you guys could have done some studies though on playing with your different variables. No.
Yeah, I agree. Another.
Yeah, if you're talking about 45 minutes to traverse, I mean, what's the size of that bed? Maybe a foot?
it's about 18 centimeters. Well, actually, yeah, about a foot. Well, actually,
You can say
Yeah,
approximately.
so if you're talking about 45 minutes to traverse that, I mean, you're generating just monstrous amounts of torque at that speed, right?
Exactly. So what's the
Yeah,
one?
so what, I mean, again, I'm going back to, you're just going to destroy parts. If you need that much torque to push something off the build plate, you're destroying the part. I can't imagine that much torque would be an effective way of popping something free.
Yeah. Perhaps I shouldn't have dwelled so much on the 1-to-27 reduction. So yeah, the 5-to-1 reduction would have been a better thing to emphasize. So with that, we would be closer to the 14-minute mark for delaminating a part. Which you're right, that is a massive amount of torque, but that's also the next sort of standard increase that was the next increment that we found on the NEMA website. I believe it went straight from 1-to-1 to 1-to-5. Is that correct?
Are you
that was
limited
no
to
sample
just
that we looked-
getting the motor? I mean, you could design a gear system to, slow that down and increase torque if you needed to.
Perhaps that was, I would argue that's a little beyond the scope of this project. But that would actually be, an appropriate response to idealize the torque ratio, so that we can get a both realistic time and not have an overkill amount of torque. I do agree with that.
And, in line with what you were saying, I think that that's something that would have to happen in much later stages of someone carrying forward with this project. it's more important that you actually find better data to show which parts delaminate and like improve the mechanism of delamination on its own before going heavily into like fully redesigning a motor to fit a part. You can't really do all that design when we're not even fully confident about all of the aspects of the ejection yet. Like we said, our best success rate with part delamination was about 80% with the PETG pieces. So
Can you guys go back to the
that
picture of the
testing, I
full
think, will take
assembly?
precedence.
The
So,
full assembly,
excuse me?
repeat that? Yeah, full assembly,
Yeah, just like that
like
conclusion
the,
slide.
right here in
Okay.
the conclusion.
We don't have a render.
Yeah,
Yeah,
okay,
first.
cool. Yeah, I was just curious if, because I thought for some reason I had remembered that maybe your like ejection mechanism was kind of offset a little bit from the print table. So I was wondering if maybe you could save some time by making it more flush, but it seems like you guys have that issue solved. So
Well, actually,
Yeah.
I
Yeah,
was
it's a
thinking that
pretty
when you
close
showed the
now.
video of it actually ejecting the part, right, early on in the presentation, there was a video of the ejection mechanism working.
yeah, can you guys go to that video?
Yes, sir. Dude. Yeah. Just give me 1 second. Let me see where it was. Here we go.
This is a good one.
Yeah, right here.
Yeah.
Right, so it doesn't look like you're scraping all the way down on the print bed, right? I mean, you've got that little bit of flashing kind of left over. Do you have a need to remove that to successfully print the next batch of parts?
Yeah, so that little adhesion, those, I keep looking there, sorry. So this little set of strings it's called a skirt. So there's different methods of adhesion, and the purpose of this is just it's meant for more one-time parts. It's not meant for mass production. So in our case, we have the capability to remove that skirt whenever we add these parts to the print queue. So every time we are printing a part, it will just be that cube that you saw. This skirt it serves a different purpose that doesn't really help us for mass production like we're trying to do.
Yeah,
Yeah,
and in later stages, we actually did remove the skirt when we were doing the automation for the
Yeah.
decode. So in later stages, we actually did remove it, and that is
Yeah.
Like, did
Yeah,
you
many of
remove
these
it
videos would
manually?
take early on.
No.
No, it
Cool.
we modified G code so that it would print without the skirt, so it would only print the actual piece
Oh,
itself.
removed it from the
This
printed
was
part.
just-
Okay, yeah.
Apologies for confusion. This was an early video from the early iteration of it before we had fully implemented the G code to remove
Okay,
the
but
skirt.
I mean,
so-
the presence of that skirt is going to somewhat depend on the design of the part, right? I mean, you're going to print a skirt on, I mean, definitely not on a cube like that, but if you're printing, something that's taller and less stable, right? You're going to print that skirt so it doesn't fall over as it's being printed.
The skirt serves a slight, so the skirt is basically you're establishing that the first layer will actually have good adhesion. So the first kind of skirt is, as we mentioned before, this little bead along the very bottom of the plate. Could you point to that?
Yeah.
This is to discharge any clogged material, and then this
Yeah.
skirt is to demonstrate adhesion. And
Serves no structural purpose in
you-
stabilizing the print.
So if you go to the cooling video, there actually is a video of no skirt being.
Oh, yeah. after
If
the-
you want to go to like maybe
Yeah,
30 seconds.
I'll skip a little bit forward as well. This was after we had
Yeah,
implemented.
see how there's no
Yeah.
skirt in that? That is part of the G code and that's automated, so.
Yeah,
it's
and
just-
I wouldn't expect you to print a skirt if you're printing a cube shape, right? I would expect a skirt to be there if you're printing, something with a higher aspect ratio that's taller.
I mean, the thing is as well, so if we increase or drop the ejector arm lower as well, we'd also risk potentially just like dragging it along and like scraping potentially the print sheet.
Yeah, well, I mean, I guess my point is I think you might need to do that. I mean, if the intent is to, be able to print parts that are going to have skirts, it seems like that would need to be removed. So there's got to be a mechanism to do that, or you're limiting the capability of what you can print, or at least what you can print and automatically eject.
Gotcha, yeah.
Yeah, so I have same comment about that one. So let's say if you print something for like aerospace design, and you need to print a fuselage like one layer, and you need to have some bring to increase the bed adhesion. Otherwise, it's like this only one layer. You cannot just like print one layer and so you need to really think about like if it's like one layer thin wall, and you need to have some like bring like this thick. bring around, how do you eject that?
I believe brims are typically used for sharp corners. So if you remember that little pyramid, that Dorito shape, that's where a brim would be really helpful. But I think with these right angles, I don't, in my experience and with our tests, that hasn't been a sharp enough corner for the deformation, which is called warping, to actually happen on the corners. At least with 3D printing in this capacity. I don't know about, you said aircraft structures, but different monster there. But
Yeah, as we said, like printing a flat, like if you're discussing printing a flat one layer thing, that would be specified for the customers not to do. I mean, at the beginning of our class, Dr. Trom and Alex even told us that like, you better not print something like that on our print farm. It's
Yeah.
not good for the printer, but we can't delaminate those if it's like a huge surface area relative to
I'm
the
not saying
height.
like a huge subject, but it's like if we need to print a wing
Yeah.
or a fuselage, you need to have one
Mhm.
or 2 or 3 layers of the brim around. Otherwise, the fuselage step is just one layer thin wall.
No, yeah, I get you. The
Yeah,
thing is,
so,
well,
I mean, do you have the capability of remove that kind of prints?
no, yeah, that kind of print with the brim, no, we would
No.
not. Yeah,
So
Yeah,
you could print it.
that's
you just wouldn't
why-
be able to automate it.
yeah, that's why we'd also need, like I was saying earlier before, it's like, since you have so many different like infinite combinations of geometries and shapes and things they could design, we'd need more testing. We just kind of did like a base set of tests just to ensure like at least if we can't get simple geometries, our thought process was that it wouldn't be able to get more complex geometries.
Yeah.
But yeah, we definitely would, for future considerations in the improvement plan,
Yeah.
redesign it as well to potentially lower it and remove the brim, I
Yeah,
guess.
yeah.
That'd
I
be
think it's
another-
better like we bring
Mhm.
more together because if you like above just put it.
Yeah, I guess our main goal at first was just mainly focusing on, okay, if we get the part off,
Mm.
then we're halfway there to remove the entire thing. But yeah, I guess we could focus on trying to lower it down more to remove the brim.
Yeah.
Yeah, and experimenting with like other part geometries and stuff, if we scaled up this project into actually like doing a bit of a startup, we could do that as like a beta testing process, allow like different people that own the printer to test it out themselves and try to like report data back to the parts and be like, hey, we'll give you all these things for free, but you need to like
Yeah.
report like about stuff for testing. So I essentially like just the more data we get from use would be required for it, but obviously in a 3-month semester, we didn't have time to
Yeah,
try
I understand, yeah.
everything.
I was just curious, yes, I understand.
So I'm also just playing this video really quickly. During the delamination process, you can see there is actually a little bit of minimal contact with the skirt. That's sort of a testament to how close we currently have it. So a good future step to sort of respond to is to add a sort of like a carpet kind of softer layer so that this arm can, make contact with this bed as it goes along, because right now we're not doing that out of respect for wanting to protect this bed. So we're trying to eliminate scratching.
All right. Did you have a like floor space requirement to fit into? Because it seems like your ejection mechanism is more than doubling the table space that you need for a printer. Is that acceptable to your customer? Do you have a design requirement for that?
It is. We had no design requirement about the assembled size. It was only a requirement about the disassembled size for transport. So it was more about like whether you could set it up in an ergonomic fashion to like run a farm like that. And that's why, as Mateus was saying earlier, we moved out. Can you see the printer model right here in the frame of the shot? That's why the goal is like if you set a bunch of these up in a print farm, you could orient all of them along a table as so. And every part would eject right here and all user control would be right here. So it's easily accessible. For someone.
Unsure? Yeah. I was just gonna say another thing as well is that you can see over here, but we did mention it. We also have this over here, which acts as like the spool holder. And that one as well, we just made it a separate piece. That way, whatever space they need to occupy, you kind of like orient it and put it like, if you need to put it up front, more towards the back, it'll work out.
Yeah, we discussed with this thing as well, since it is kind of large, like there was a potential idea of modifying the back plate to include a spool holder or something like that. You could possibly integrate that thing. I mean, a lot of spool holders used in even our print lab here at UF are just pulled from GradCAD and, find whatever is like best used for your application of your own print farm.
Okay.
But yeah, the
And
table space
can
was
you go back
not a
to-
customer requirement.
Can you go back to slide, I think it was 14?
Gotcha.
And the presentation's not being shared anymore, by the way.
Yeah, we're
There we go,
reshaping
okay.
it right now.
Sure.
14, you said?
Yeah. Yeah, we're looking at the folded up thing in the case.
Yeah.
I remember seeing in the customer requirements, and I'll admit that this was eyebrow raising, but I remember seeing in the customer requirements that you were asked to survive a 15-foot drop in the case. Is that still a requirement?
Well, yeah, that's something that we've been discussing with the customer ourselves to see if that was still within the requirements.
And with Dr. Nimi, because he doesn't want us to break his minis.
Yeah, we switched the printer from the original printer to Prismini, and Prismini is owned by Dr. Nimi, so we don't want to drop it without his permission.
I'm sure you don't want to try. Who wrote that requirement? Because I remember the shaker table project last year. I think Dr. Nimi had a drop requirement that he was asking for.
Yeah, probably me at some point. I really like dropping things off of buildings and.
Oh, I mean, I fully support you dropping Dr. Nimi's 3D printer off the top of the building, but I don't think anything in this case is going to survive that drop.
We can disassemble the printer right now and put it in a case and do like
That's good.
Yeah.
That's it. That.
Oh, yeah, well, first let's see the other questions, then we can maybe do it toward, yeah, let's not get too excited.
I mean, I'm interested.
Is there any questions people were disassemble everything?
Oh, are we done with the drop question?
No.
We're gonna do.
We're gonna do it again after the questions
Yeah.
that they may have.
Yeah.
Well, I mean, I thought that we agreed on.
He's serious. That's why we got the case we did.
Actually, it's probably,
You still considered the customer requirement, but.
don't do it. All right, we won't do it. But we could have. That's the reason why I bought the protective case over here. It has like foam lined along the inside as well.
Who needs to buy the new one?
Yeah.
Yeah. All right, so we won't do it for now, but if we wanted to, we could
I'll
try it
have
out.
to deal with Amy if it goes wrong.
All you guys.
So I guess to provide some clarity, the shaker table drop requirement came from Professor Menezes. Because he had who was the microbioreactor customer, who had an issue with a grad student that accidentally knocked like $100,000 piece of equipment off a lab bench and it smashed onto the ground, and he was very cranky. And so he added the original requirement for the shaker table was it had to fall out of an airplane. So he wanted to basically reach like sonic velocity and hit the ground and survive, because he had such a bad experience with
Oh
this.
man, he must have been pissed.
So that requirement kind of got propagated forward into this set of customer needs for kind of the same reason, right? Because you can imagine we're talking about like a pop-up print facility where people are just trying to assemble these things and get them popped up and get them printing as quickly as possible. And you can imagine somebody inadvertently, accidentally knocking one off, from the top of a 3D print farm scaffold, which is like 12 feet, 15 feet above the ground. And so that's where that requirement came from.
Yeah, I mean, I can certainly imagine, if you're asking, FedEx to ship one of these, FedEx is notoriously not particularly careful with their packages, right? So, but I mean, even here, right? I mean, the way things are laid essentially loose, like even if this gets shaken around, things are gonna rattle, things are gonna come out of tolerance. It seems like the packaging aspect of this project, there wasn't much attention given to that. And I agree, like designing something to survive a 15-foot fall is maybe a little aggressive on the design requirements and can be pushed back on, but I don't think this thing is going to even survive normal shipping the way it's laid in this case.
Yeah. Well, and we just wanted to show as well, it doesn't just lay, we did cut out foam inserts that do support the parts within the case.
So it's not loose at all.
Knit around stuff, like it's not loose and it hasn't rattled, like when you guys put it in the case, it wasn't shaking around or anything.
Yeah, so because in the picture you're showing in the slide is a previous version of the. package.
Yeah, that was before we did the cutouts here to fit the things in its folded form. So now it has some type of integrity within the case. But I do, that is a very valid concern. If it's loose in the cakes, it kind of serves no purpose for it to be a padded thing.
Okay. Can we take a look at the structural analysis? I think it was on like slide 20 or so.
Yes. With the antlers first?
Yeah.
Okay.
Well, either one. So here, one of my constant complaints in these presentations is you guys go and calculate a factor of safety for your part. What's your factor of safety requirement?
I don't, there wasn't a factor of safety requirement.
No.
You didn't have one? Would a factor of safety of 1 have been acceptable?
A factor of safety of 1 likely would have been acceptable. I mean, the part that has never failed on us, but.
Yeah. So I guess my point is, right, if you're calculating a factor of safety, you should have something going in mind of what an acceptable factor of safety is. Maybe that's a customer requirement. Maybe that's something you impose on yourself. To me, if you're saying, you know, I've got 3 times my capability, or three times capability is what I actually need. To me, that's very acceptable. But the idea that, you know, if you come up with like, you know, 1.2, and like you don't have a criteria for it, right? So it doesn't make sense for me to see it without an associated criteria here. So I would encourage you to approach factor of safety as a design requirement and not just let's see what we get and decide after the fact if that's acceptable or not. The other thing I would talk about here is, I mean, it's without seeing like a free body diagram of you know how things are loaded and what's going on here, the structural analysis is very difficult to follow. I think I'd noted down like slide 22 when you're doing a cantilever beam analysis.
Yeah, I'll go to 22.
Yeah, I just don't know what's going on here. I definitely don't see any moments, and I'm pretty sure that as this thing is loading and pushing a part off of a print bed, you're going to induce some moments because loads are not aligned with you know the parts that are being loaded. So I don't think you're considering the loads appropriately, but again, it's tough to tell without any sort of free body diagram.
And so this cantilever beam calc was also like not,
It's a deflection calc.
yeah, it's a deflection calculation, so it's to ensure that.
Are moments going to cause deflection of a beam?
I'm sorry?
Are moments going to cause deflection of a beam?
No, they do. I'm saying it's not about the calculation was focused on the moment, it's on the thing while pushing parts. It's ensuring that the actual print arm stays in the correct position throughout the thing and that its own weight doesn't cause it to overhang over.
Okay, so if you need it to stay in the correct position, right? I mean, if you're worried about, oh, you're going to drive into the table and start scraping the table, right? I mean, as you load this thing up, depending on where your force is being applied versus where it's being reacted, you're going to bend your pusher, and you're going to, you know, load up the rail that it's sliding on, right? And I don't see any consideration of any of that beyond, I guess it sounds like you're talking about self-weight. Even self-weight, right? You've got this big overhanging beam, right? You're going to have a moment created by that self-weight. So I don't think that what's going on here fully captures what you're trying to achieve.
Well, if you're talking about the moment, there is force and the length of the beam as functions of the equation. So that's where.
Yeah. So I mean, though, if you're talking about the force as like the you know applied at the CG, but like the force of actually pushing something off the plate isn't being accounted for here.
That's
That's
perpendicular to the.
That'll affect the motor driving the actual ejector arm itself.
That's parallel to the deflection line. So the force going forward isn't really.
Right, but the force of that actually pushing on something is going to be applied off axis with where this thing's being supported. Right, it's being supported on the rails. It's being driven on that drive screw, and then it's pushing at some distance above that. You know, whether it's contacting near the bottom of the print bed or it's, you know, contacting further up on the face of that. Right, you're going to be inducing a moment into whatever this thing is being supported by.
Yeah, like it would try to push this up and this is not on the line of action, so it would. I understand what you're
So
saying.
we should have shown that the motor or the ejector would fail, which one would fail first, depending on that
Yeah.
force.
I think there is mistake in calculation on page 17.
Uh-oh.
Yeah, so there is a mistake, the BH cube, YH equal to C. YH equal to C equal to 0.5.
So maybe this is kind of like,
It's
Uh,
rectangle cross section, right?
it's kind of rotated from like VAC being calculated on it. I did see as like half of this thickness. Would C be like in this direction?
That doesn't pop off.
Oh, okay, never mind then.
So if it's a rectangle cross section, H equal to double C, that's
Yeah,
what I mean. But right now in your equation is H equal to C. You know what I mean? BH cube, H is it's like depending on which direction of bending,
I
there
see.
is a high
You're right.
direction. So it should be double the C, but right now your H equal to C. So
Okay.
that is a
So
mistake.
the C is correct, the H should be double.
Yeah,
And then I guess if the H is double, then the I is bigger, and then that would actually mean that the,
it's actually less.
yeah, it's actually. Great.
yeah. So I'm really surprised that if in your situation, you calculate this way and in the end, you subtract 3 because it's really like in real situation, you subtract should be much higher. So the calculation here is wrong.
Yeah.
That's
should
what I
be.
mean. It's like H cube should be 5 cube.
Should be double what we calculated.
Or more because it's getting.
Oh, yeah, so, yeah, never mind.
Eight times.
Eight
Yeah,
times
you're right.
four, yeah.
Yeah, that's what I mean.
But it's wrong a good way to.
Yes.
We knew it worked, so it couldn't be that much lower, but yeah, it should be higher.
So when you see the same pattern, you should like really question like if calculation is correct or not.
Well, the factor 50 would have been higher if the moment of inertia was correct, so.
No.
Yeah, we should have looked over it with fine tooth comb.
It's not like it was an intentional.
No, I'm just saying it
assumption.
wouldn't raise even more questions, the factor 50 being that high.
Yeah, like when we were looking at like the flanges for this, like we took an assumption like as if the flanges were the sole support of the weight. When it was actually even some of the weight supported by the riser and by the distributed load of the inside of this 80-20.
Yeah.
We took like a worst case scenario assumption, like if only the 2 flanges were supporting the weight of all of this, would they still be structurally sound? But that's not an intentional assumption, that's just a mistake. So thank you for pointing that out.
What?
Were you sitting on that the whole time?
Pretty well.
Sitting on it.
Like you noticed it from the beginning of the presentation.
Yeah, when I was so C and H, I knew. So I'm very sensitive to the
No, but it's good that you pointed it out. We'll fix it.
We appreciate it.
sometimes I'm gonna wait.
We submit the notes.
Yeah.
Yeah, any other
Maybe
notes?
you guys. Maybe you guys went over this already, but where is this 30.2 Newton force coming from?
Nick, I believe that's the right from your
That's from the
calculation.
motor,
Your
right?
motor cap.
Yeah, I guess, can you go to the
The last
last slide?
Yeah.
Do we have it in the calculation was included?
Oh,
Yeah.
you mean this?
I think that was in the
plot?
report. So, yeah, this is it, thank you. Yeah, so you said 30.2, so that was, the calculation to get that number was included in our report, but this is the plot that we were, taking that from. We were running at, I calculated it at 150 RPM. Like I mentioned earlier, I said something about how we're getting 80% of our expected torque. Sorry, I said 120 RPM. We're getting about 80% of our expected maximum torque. And using, because we are running with the orange line right here, so we're sitting at about here and using this torque of about, I think it was 0.47, and using a series of calculations that are included in our final design report.
Yeah, like a
That's how
picture
we-
of the lead screw and everything.
Yeah, it's taking into account the picture of the lead screw and the torque, and
So it's essentially like the max force output from the motor that
Correct.
we currently have it set up. So we did all those force calculations using like the maximum output with what we currently have set up. They would have to be redone if we did incorporate a more powerful motor as we would like to do in the future on this project.
Yeah, that's kind of what I was getting at, because I know you guys had talked about you guys are doing, trade studies in the future, so I didn't know if you had considered like, okay, hey, if I swap out, to a higher torque motor, like what's that going to do to all of my interfacing parts? I mean, you guys are looking pretty healthy on, factor of safety as you guys showed before, so I don't think it's a massive concern, but just something I was wondering if you guys could or had considered, and where those values were coming from.
Yeah,
So.
no, we had considered it, considering that, I don't know why I said that twice, but I mean, just since we were also discussing using other motors, like we've been considering the other like force increases on it for the last while, like a good minute, we've been discussing this.
Weeks.
Yeah, weeks.
Can we go to the cost slide?
Yeah. You want the hourly rate breakdown or the prototype?
Just the cost, yeah. So are we talking about the cost to build one prototype, right? Like that top line, that $1,000 line, what is that specifically covering?
Yeah, so this one over here for the assembly kits, the total consumable material cost, like I said, it would be the thumb screws and the fasteners here, the electrical box. The filament to print the new electrical box, back plate, front plate, fan clip, display, ejector arm, the motor mounts, the lead screw, the sleeve as well.
Case too.
The case as well. The case is for the pre-built printer price. Pre-built printer price also includes the case, the price of the original printer itself. Total consumable as well, going back to both of them also have the price of the NEMA motor itself, lead screw, all the electronics, the wiring. And
okay, so for $1,000, I'm getting a kit that I would add on to an existing printer.
yeah,
Okay, did you have a budget? Like what were you trying to achieve?
yeah. So okay. Yeah.
So it's, noted with the budget, we stayed within our budget to make this project. We had a budget of $250 for.
Oh no, I'm not talking about for your prototype. I'm talking about like what did you expect a customer to pay for one of these kits, right? I mean, you're saying you can essentially sell them for $930 at a production run of 10, right? So the customer's essentially buying an automated ejection mechanism to add on to an existing printer without any other sort of capability, or they can buy a $2,000 ejection mechanism end printer from you, right? So if you're adding $1,000 to the cost of a printer, is that what you were targeting for the cost of your device?
Yeah, we thought it'd be original because the assembly kit not only does it allow like automatic ejection and like to use the printer as kind of like a print farm scenario. It also gives the user the aspect of foldability for easy transport to things that aren't unanimously, both aren't offered together in the marketplace. And as we say for one of our competitors for the print belt system, that one was listed to be around $3,000. So for something like this, that's about third of the price. You're getting an automatic ejection plus foldability. We thought it was a reasonable amount to charge customers.
And yeah, we also did discuss the fact that if that
what was the requirement you were working to?
we had discussed.
For a selling price, we didn't have a requirement. We only had requirements more of a budget ourselves for the actual pieces that we ordered to assemble the printer.
We wanted it to ideally.
So you had a budget that you had to work within to complete this project, but you didn't have a target price for your product?
No, we didn't.
No.
That's interesting. Do you think you should have?
I mean, we operated trying to keep it as close to what the cost of one of these Prusa minis would be on its own, which I think these retail for like
$400.
$440,
$40 if I'm not mistaken.
So we did exceed that, and I know that
So how do you gauge the reasonability of that, right? I mean, if you say, hey, we're going to offer this automatic ejection mechanism for a printer, it's going to cost as much as the printer itself. Like, how do you evaluate whether a customer is willing to pay that?
Yeah, and it would take a lot of market analysis. Like
You had us well.
Yeah, or like I was saying before as well, for example, the belt printer that we'd seen before was $3,000. So if we take into account our one prototype of the assembly kit, if they were to buy this, plus they bought themselves the individual printer for about $470, that'd come out to about like $1,500. That's about half the price of the print belt print off the
Yeah,
printer
maybe
from
competitors.
competitors.
And the other thing too is if we did want to reduce costs to provide a more budget version, it'd be possible to only sell customers essentially access to all of our. I mean, it's kind of interesting to do that as like an open source thing. I know we talked about that, but like
Have
they
you-
could
can I-
print
can I-
some of the
can I
parts
just
themselves
can I
and
stop
only
you
give
real
the
quick?
electronic equipment.
Can I-
Yes.
can I- did you read your customer requirements?
Yes.
Because your customer requirements explicitly say your part ejection modification cannot cost more than $250, and your modularity modification cannot cost more than $250.
So on that count, I know the price over here doesn't match it. I can explain real quick. For that one, we had assumed that the $250 price would be purely just for the materials for this project and this class. And the price over here, it does go over, well, this one over here, just the assembly kit does stay within that budget of total $500. And it'd be lower. as
I don't
well
know if
for
that's a reasonable interpretation of the requirement.
Yeah, we actually did discuss this with the client and that was reasonable. It was our budget for the cost of production for the project and for the cost of prototyping. So we stayed within that budget for all of our design work the entire semester through the project. The reason that the cost doubles is because we all work with unpaid labor. Had you actually had this done in production and had to pay people to do it, then the cost would go up.
Yeah.
Oh yeah, I mean, I
more than
agree.
double.
I think that the R&D cost, the development cost of your project is very much subsidized by you guys working for free. But to me, in a customer requirement, if there's a cost, right? I mean, the customer requirement is not, hey, you've got this much money to develop your project. The customer requirement is, I want to be able to buy this product for $250 or $500 for both major features, right? That's what the customer requirement seems to be getting at. If you went to your customer and you said, hey, we're actually coming in at around $1,000 per unit, is that okay? And the customer says, yeah, that's okay. That's a thing, right? That's modifying the customer requirement. But as I'm reading the customer requirements, you essentially doubled what they were looking to spend.
I mean.
Hey, real quick, Tom, if I could clarify something just real quick. So in the beginning of the project, when we gave them the original customer needs statement, it was with the focus that this would be something that the lab spends money on to kind of outfit some of their printers to have this capability. And so it was less geared towards designing a product for customer use. And so that original design requirement was for the production of our lab to be able to make more of these things. And so that's why in the beginning, it was designated towards a strict, like no profit build cost. And as the project evolved, then the team started to look into what would it actually look like if we were to sell this to outsource or outside customers. And so it kind of evolved over time. With the original customer needs statement that was developed by us was specifically for our lab for nonprofit. If that
So you're
clears up
talking
any
about
confusion.
with free labor, is that you're meeting the customer needs because you're not paying for labor and you're only consuming $480 worth of materials?
Correct, and it would continue to be developed by
Okay.
further students and further iterations in the scenes of like research projects, undergraduate, researchers and workers and such.
Okay.
Are there any other questions or any other slides that you guys would like us to go back to and look at?
Nothing here?
Nothing here. Appreciate it, guys.
Awesome.
Thank you for attending as well and giving us
Thank you.
feedback.
Yeah, appreciate you
Appreciate it,
attending.
guys.
We like the feedback.
Oh, are we?
Oh,
wow,
this is fun.
Yeah.
This was great. I love this so much. Do you guys feel like you created something of value this semester?
I'd say so, yeah.
Yeah, we had a full semester, I think it would have been a lot more value, but I think we did a lot of it.
I mean, considering short semester and also we kind of were working from scratch, I'd say.
Yeah, we had a.
Yeah,
Designed to come up and out.
Yeah, I think we definitely took a step in the right direction.
Yeah.
With where we want to stay.
Yeah, we hit the brick wall like 3 times.
Yeah, I mean, it was
Like the
for
first
us,
6 weeks.
for us, it was just that constant cycle of, okay, potential design, looking into it, costs, and also working it with the biggest actually like. The biggest like trouble with making this was originally with the MK3S Plus was working in foldability. With the auto ejecting parts, because like it's easy to do the MK3S just purely foldable, like you could kind of cut the bars over there, fold onto itself, but then if you add ejectable parts and also have no loose fasteners and also like no tooling required from external customers, we're kind of like stuck there thinking it's like, okay, we can work with hinges later on. We eventually, once we switched to the mini, only then did we realize we could use thumb screws as potential like no loose tooling to get around that, and also the fact that the customer would need screwdrivers, Allen keys of specific size and things like that. So it was more of just a constant struggle to meet both requirements and also try to keep budget into consideration as well. So I'd say for all that, starting from scratch, kind of and staying within relatively the budget, I'd say we did pretty good job.
And I think we learned a lot in that process too.
Yes.
Like having
Yeah.
to deal with so many needs that didn't necessarily have any synergy with each other. Like it was a very interesting design process.
Yeah, so this is like one of the beauties of Capstone, right? Is like you run into these like very real world problems that you don't find in like any other class. And it was just like really awesome. Like although, you know, it was definitely a struggle for you guys at times, and you know, it's tough being the guinea pig of a project, but we really appreciate everything that you put into it this semester. And I think you definitely did create something of real value that in its current state can work, and in future iterations of future students iterating on it will really create something that is a pristine piece of technology that hopefully can get further propagated into, you know, our future lab spaces.
Definitely.
So again, I just want to thank you guys so very much for everything that you put in the semester.
No, we appreciate it.
Very-
Appreciate it. Thank you.
It was honestly a great experience.
Yes.
And honestly, I think we have a good jumping off point for future teams to work on. I feel like that's the.
Yeah, sure.
That's the best thing.
Yeah, and also one thing I want to comment on is that overall really great job in purely in terms of presentation today. I really like the style of the slides. It's like, well, this one is like because it costs
this one's-
separate, but for the rest of the they are very comfortable to read. So I think you know what I mean, because in the
Yeah.
first class, I spent like 1 hour talking about how to do the presentation, how to prepare slides, and like so many crazy slides.
Yeah.
And this is really the style that I really want to see for every presentation, but it's like something just ignore my opinion. So I think in terms of the slides, it's really good. I really like it. And also in terms of presentation, I think you guys are really like trying to communicate with us. So it's the presentation style is also good. And yesterday, I think I commented on one student, a girl, because he was not that confident. It's like facing the screen all the time, like voice was shaking, but it's not her fault. But I mean, it takes practice, but I think today's presentation is really good. And I could feel that you guys really want to talk to communicate with us and try to explain everything. So purely in terms of presentation, in terms of slides, I really like it.
Oh, that's great. Thank you very much.
I do have one thing to say about the slides, and this was like the first thing that Mr. Singer said, is that it felt almost a little backwards, where you had all of the performance evaluation data in the beginning and then described what it was. So that like it really like I followed it because of course we're the customers, but in the future I think it'd be a lot beneficial if you start like, this is what we're doing, this is what it is, then this is how it performed.
Yeah, I think we're just too
yeah,
deep into it to
Yeah.
consider like an out of world perspective.
Yeah.
Of course, yeah.
Yeah, we were just kind of like, let's get all this information here, and it makes sense to
Yeah.
us.
Of course,
I
yeah,
mean, we were kind of doing the slides for like a day. I mean, since FDR and everything was on.
of course.
through the day. So we were just like, yeah, we gotta have everything in here and we gotta practice the presentation.
Yeah.
Got a little too wrapped up in it.
Of course, that happens, yeah, but. No, really, I really appreciated the slides past the conclusion slide. That's something that.
I like the addition on, yeah, I mean, we also had, we didn't mention it, but we had included like
Yeah.
the circuit diagram as
Oh,
well,
yeah.
but I guess it never came up.
No, because this is something that I think the other group didn't have, that they could have benefited from just having.
Yeah, this was something I learned from, actually, it was Aero Design 2 presentation as well. It's like, for the Q&A, yeah. It's like for the Q&A, it was very important in that aspect as well. We had more calcs to focus on. So to not clutter up the actual presentation,
Right.
but to leave more resource to where you won't say, oh, we had this one graph. What I would recommend as well, maybe for future classes, was to tell them is like, have their final slide, like that, and then right after that's like any graphs, plots, images that they think they'd want to bring up during the Q&A to add afterwards as additional info slides.
Absolutely. Do you have any other slides back there? Or is
No,
this
it's just those two.
We had the motor.
We had more, but we deleted one.
Yeah,
I mean, that was
That was
sufficient.
every project.
That was up to us. That's where it literally like internalized the fact it's like, oh, less words.
Yeah.
Let the images tell a story and let this presenter be the narrator, not the other way around.
Yes, it's like every sketch design class, I always spend 1 hour talk about what kind of slides I want, what kind of presentation I want.
Yeah. The only other thing with the slides is I think the hedgehog concept slide, the text was kind of small to read from back here.
Yeah, we could,
But,
we
I mean,
take some of that off.
Yeah, no, I understand. Do you have anything else?
Yeah. You guys want to see the drop test?
Well,
Drop test.
Let's call Sean.
They didn't even come outside.
What's the biggest thing that you?
We didn't ask them that, well, you sort of asked them that final question.
Oh, I think they already addressed it in their presentation.
Really?
Yeah.
I don't-
So normally at the end of like every capstone presentation, my big question is, if you were to start completely from scratch, like coming back into Mech 3 again for a second time, which, won't happen. to you. It's not a question of, so if you were to start completely from the beginning, do you think that you would end up at a design very similar to this? Do you think that this design is in the direction of the most optimized design to solve the problem? Or do you think after having this knowledge, it would go a completely different direction?
I think it would stick very similar to what we have right now.
Yeah.
The only change I can think of is a different driver and a better motor.
Personally, I want to go back to the original printer and add bending to it, so we have a higher chance of delineating the part. But everything else just stays the same.
Yeah, it's like all the other solutions that are potentially more reliable or like more elegant, like Dr. Newman really wanted us to do the garage door thing,
Right.
but then even he was like, oh, but there's no way you guys can get this to be functional within 2 months. Like,
Yeah, especially with.
so within the constraints, I think this was the direction that we probably.
Definitely the foldability is
Yeah.
best.
Slide for the garage door not working?
Yeah, we had a
No,
slide.
Then it was a discussion that we had.
Yeah.
We had come up with like the bending as well. That one I don't think we have.
Oh,
but
Yeah, we want to
Yeah,
have
we didn't have
bending, but there's no more room on the cruiser needed to add bending.
yeah.
Yeah, absolutely.
Yeah.
So this was back when we were doing with the original MK3S Plus.
Right.
But yeah, that one as well is just an issue of like, okay, so for example, if we had done the foldability with the MK3S Plus, we were planning to just get the, like, over here, we have the L frame, we had a U frame, folding it down, but then it would fold down onto like an ejector arm,
Mhm.
for example, or even if we did like, well, I guess, yeah, the ejector arm over there. You're gonna put it into position. If we put it in the front plate, it would like land on top of it, it would like collide with it, it wouldn't really fit like a nice volume. The way that we made it right now, where it kind of detaches, it fits nicely, it doesn't take up too much volume compared to if we did the MK3S Plus. I think we're talking about we'd get like a 2 foot by 2 foot area and then an X amount of height that we had to deal with. So
That's okay. Yeah. No, that's good.
Because without the oversized case, I mean, if this thing, it fit into like one of those like black boxes in the lab, like one of those
Yeah.
little black,
Yeah, it's
those are pretty good.
Can you put it in the case?
yeah. Oh, you want video?
Oh, yeah, we could.
No, you do. I
Oh, you got time? All right.
Wait, you just want one,
case closed.
can I do the
Start the
wire?
case closed.
Do you just want one person doing it or?
Or the one person?
However fast you can do it.
All right.
He goes down.
I should pick up.
Okay. This is loose. Like a stick for.
Like NASCAR thing.
There you go.
That's it. Yeah, keep it going.
All right, let's keep it together because ones.
Yes, sir.
Got it.
That part.
So do those not go in there? Oh, because in the future, they're already on there.
Yeah,
Which they are on there, but.
Right. Well, I understand, yeah.
yeah, it's like the final cleanup of those things.
Spool holder down there.
Well,
On the outside.
Yeah, we don't.
like a cheap,
That's so then cool.
and
I dropped this. No, you got it.
Well, drop it.
Someone call Dr. Neiman.
I wanna see it drop.
We can drop it from the table or out the window.
I mean,
We could, I think it'll survive.
Is someone below us? There's only one.
No, that's insane.
I've never felt it, can I feel it?
oh,
No, it's not. I kind of.
It's ergonomic.
A little bit.
12 kilograms, 26 pounds.
Like a staring at
so,
suitcase.
Tom, I don't know if you can still hear us, but now we're into.
I'm very eager to see this.
What's that?
I'm very eager to see this 15-foot drop test.
Let's do it.
I mean, that does show ultimate confidence in your design if you do that test live. This is Elon Musk throwing a baseball at the window of a Cybertruck.
Exactly.
I mean,
Let's
like I
go.
joked around, we paid lab fees for a reason, you know, if we break a printer.
It will.
You're just trying to keep getting in trouble with the department.
Yeah.
I'm trying to get him a new printer.
Yeah, I
That's not 15 people.
I don't know. The only thing.
We have nothing to gain from. Why are we taking?
No, I don't want us to do it,
This for personal satisfaction.
but I'm winning the battle.
I think so.
Well,
What's-
let's take it back to the lab and then we have someone hold it up and just drop it on the floor.
Sounds good.
That's 6 feet.
Yeah,
You want to go?
don't drop it on the floor.
So we gotta stop screen share.
Sorry.
I'll take it out later.
Yes, sir. No, Tom, I don't know if you can hear me, because now it's a little
Yeah, I
chaos.
got you.
We're, I think, gonna actually take it back to the lab and drop it. So we'll
Oh man, get video.
take a
I wanna
video of
see it.
that and see what happens.
All right, good luck, guys. Good luck with Dr. Nemi after.
Sorry, I can't hear you over the.
I said good luck with Dr. Nemi after you drop it.
Hang on. Give me 1 second. So, sorry, I missed almost everything because of the noise in the background. What were you saying?
I said good luck with Dr. Nemi after you drop it.
Oh,
Thank you.
yeah, thanks. Yeah, that's it. If it survives, we don't even have to tell them. So,
Yeah,
anyway, thank you for sitting in and asking questions.
sure thing. All right, have a good one, guys. Go Gators.
Okay, thank you.
We're going back to do the cleanup. Do you guys want us to reassemble the